Welcome to section 4.2. We'll be looking today at parabolas and their applications. So in the previous section, we learned how to solve quadratic equations, and that's going to play a major role in what we do in this section. So if you need a refresher, make sure to go back and watch that video on section 4.1. Look at the various techniques for solving quadratic equations and consult the notes for the procedures that are written out step by step. So the notes for this section begin on page 54. We are dealing in this section with any function that can be written in the form f of x equals ax squared plus bx plus c. Now that's not the only form that we'll encounter, but that is what we call the standard form. Now, every equation or every function in this section is going to be based on the graph of our basic y equals x squared. So our graphs in this section are all going to resemble y equals x squared, potentially with all of those transformations that we saw in chapter 3 applied to it. Our first sort of manifestation of this transformation, if we have a parabola where a is greater than 1, or greater than 0 rather, our parabola is going to open upwards. We'll say it's concave up. Just like y equals x squared, which has a positive leading coefficient. On the other hand, if we were to tack a negative onto the front of x squared, if we change this 1 into a negative 1, our a, the leading coefficient, the coefficient of x squared, would be negative, and that results in a vertical flip. So at the very least, when we first encounter the equation for a parabola, we can tell right away whether it opens upwards or downwards. In other words, whether it's concave up or down. Now, in the case of a parabola that's concave up, the feature that we call the vertex, the turning point where our graph changes from decreasing to increasing, is a minimum. On the other hand, for a concave down parabola, one that opens downward, that vertex is a maximum. Now, in mathematics, that word vertex gets thrown around a lot, and it really just means important point on some graph. The important point on the graph of a parabola is this either maximum or minimum. And the reason for that is that that is the point about which the parabola is symmetric. So if we were to look at the graph of y equals x squared, try to graph it as best we can, this parabola is symmetric with respect to the y-axis. In other words, if I were to flip the graph across that line, x equals 0, the resulting picture would look identical. Now, if we go and move a parabola around in space, maybe we move it over to the right, and we'll flip it vertically, it's still nice and symmetrical, it's just no longer symmetrical with respect to the y-axis. If we were to flip across the y-axis, we would end up with a graph over here on the left. So that is not the type of symmetry we're observing here, but if we flip the graph itself across that line which passes through the vertex, we would see the resulting graph would look identical. This thing has mirror images going off on the left and on the right. So we call this line, the line through the vertex, the vertical line through the vertex, the axis of symmetry. Now on the next page, there's a discussion of the notes. There's a discussion of the concept of intercepts. So remember, an intercept is any point where a graph crosses either axis. So if we look at the graph of a parabola, just make one up. Okay, we see that this one has two x-intercepts and a y-intercept. Now in the notes it says that every parabola will have a y-intercept, and that's because the domain is all real numbers. So our function is doing something when x equals 0. There is some point on the graph with an x-coordinate of 0, and that point is our y-intercept. So to find the location of the y-intercept of a parabola, or a quadratic function, all we need to do is evaluate f of 0. And we see that every piece of the equation, of the formula that contains an x, those terms all go to 0. So we have 0, 0, and c. So very similar to lines, the constant term tells us the location of the y-intercept, in this case 0, c. Now finding the x-intercepts is usually a bit more work. To solve that, we would set the equation ax squared plus bx plus c equal to 0. So here we have the argument for the y-intercept, and here we have the argument for the x-intercept. And I should say x-intercepts, because our parabolas can have up to 2 x-intercepts. Here we see a graph exhibiting that behavior. If we look back at the graph of y equals x squared, we see there's just one x-intercept. And to see an example of a graph which has no x-intercepts, we can take y equals x squared and move it up a little bit, and maybe move it around horizontally. So we see this graph has no x-intercepts. Alright, so once we set up that equation, that quadratic equation, we can use all of our usual solution techniques from the previous section to try to solve. We could initially examine the discriminant to determine whether there even are x-intercepts, in other words, solutions to this equation. Or we could just charge straight ahead with whatever technique seems appropriate. I generally like to try factoring. If that doesn't work, maybe the square root method will work. Failing that, I usually go straight to the quadratic formula. That one will always find our solutions to this equation, even if those solutions are non-real. Now here we see the standard form of the quadratic function. I would like to justify the statement made in remark 4.1, which says that another way that we can write this is represented there on the page, as you'll see. So the way that we arrive at that conclusion of remark 4.1 is by completing the square. So the first thing that I do with this right-hand side is I factor a out of the first two terms. So to do that, I'll bring a out. When I factor a out of ax squared, I'm left with x squared. When I factor a out of b, I'm left with something a little strange. I'm left with b, and I have to divide by a to compensate. Okay. So now I'm going to complete the square. I'm going to take the coefficient, now that I have a 1 in front of x squared, I can take that coefficient of x, b over a, and divide by 2. And I'll square the result. Alright, so b over a divided by 2, that's the same thing as b over a times 1/2. So what are we really hoping to add in order to complete the square here in brackets? We need to add b over 2a squared. So that's what I'm adding inside. Now, if I add this quantity, that changes the formula. So I can't say that this is equal to a times x squared plus b over a x plus b over 2a squared plus c. I have added something. So at the same time, I'll also subtract it right next to the place where I added b over 2a squared. Okay, so essentially all I've done is I've added 0, but I've done it in this slightly strange way. Okay, so let me rearrange things a little bit. I have a times x squared plus b over a x plus b over 2a squared. And that's a perfect square, but I also have this minus b over 2a squared. So I'm actually going to multiply that by a and bring that outside. So every step of this is justified. I have not changed my equation at all. I've just modified how it looks. Alright, now the stuff in brackets is a perfect square, and since I completed the square, it will factor as x plus b over 2a quantity squared. Okay, that factorization works because I chose this particular number to add. And now I'll just simplify the stuff on the end. Minus a times b squared over 4a squared is another way if I apply the square. Alright, and if I combine some like terms, get a common denominator here, I won't be messing with that x plus b over 2a quantity squared. I'll multiply the a by the a in the denominator. That gives me b squared over 4a. Now I want to add c to that fraction. I'm going to need a common denominator, so if I multiply by 4a and divide by 4a, here I've got c. So finally we could write this as a, let me switch to parentheses, x plus b over 2a squared. Let's rearrange things a little. If I do the plus 4ac minus b squared over 4a, I can now combine those two fractions into one since they have a common denominator of 4a. So this form is what we see on the other end of the spectrum there in that remark, in remark 4.1. Now why is this useful? Well, if I think of this stuff, this is just plus some number. I'll call it k. And here I have a times x plus some number squared. Alright, so I can recognize how the graph of ax squared plus bx plus c will look in relation to the graph of x squared. These are all transformations. We have a causing either a vertical flip, if it's negative, and possibly vertical compression or stretch. Our number here inside the parentheses, here I have x plus a number, that is going to cause a horizontal shift. We're going to shift negative in the negative direction. So if this number b over 2a is positive, if I say x plus 3, for example, that would shift us in the negative direction 3 units. So we're actually going to move towards negative b over 2a. And finally, our plus k plus this big number on the end is just a vertical shift. So if we write it in this form, we can see the transformation taking place, in particular to the vertex. So our original vertex for our function y equals x squared is located at 0, 0. Our vertex, if we modify this function, if we're dealing with a transformed version or a generic quadratic, this is a nice form for it to be written in, but we could write that as a x plus b over 2a squared plus 4ac minus b squared over 4a. This quadratic is going to have a vertex at opposite of b over 2a, and the y-coordinate is going to be shifted up, so that's going to be at 4ac minus b squared over 4a. Now generally, to find the vertex, you would find the x-coordinate first as negative b over 2a. Here I'm talking about a and b from the original equation. And then once you have that x-coordinate, plug that back in for x to find the y-coordinate. So that is what is being detailed there in Theorem 4.7, how to find the vertex. Now this whole process, deriving the theory behind the vertex, is not essential. You don't need to do that. It is a procedure that you may use in the future, particularly if you want to find the vertex for a parabola and you forget vertex form. If you know how to complete the square, you can always figure out where the vertex is. But this is just the first situation where we can use completing the square to find out useful information. So the first actual example I would like to look at is going to be solved using the calculator. So given function f of x equals x squared plus x minus 6, we are going to find the vertex. We are going to state the domain and range. And finally, we are going to find all of the intercepts graphically. So in your graphing calculator, we're going to type our function into the y equals screen, clear out anything you've got in there already. So our function, x squared plus x minus 6. And I will go to graph. If your window is maladjusted, you can always zoom standard. Alright, so here we see a nice parabola. It's concave up. We should know that based on the coefficient of x squared being 1. We see that this parabola has two x-intercepts and we see our y-intercept. So this parabola fits nicely into that standard window. So the first thing I want to find is the vertex. And I'm looking at this graph and I see that the vertex is a minimum of the graph. It's the lowest point on the graph. So I will second calc, go to the calculate menu, and I want to find this graph's minimum. So I'll go a bit to the left, a bit to the right, and I'll guess somewhere in the middle. My calculator is giving me an approximation. It looks like our vertex is at negative 0.50000016, or something very close. I'm getting a little bit of a rounding error, but I feel safe in assuming this is actually 1/2. And our y-coordinate, negative 6.25. So what I can take away from that is that negative 6.25 is the lowest that my graph ever gets. So we can move straight into the question of the domain and the range. Well, the domain for parabolas is always going to be the same, all real numbers. You can plug any real number into this formula and you'll get a reasonable answer. You'll get a real number as a result. Our range, however, is going to be restricted. Our parabolas have low points and high points. So our range begins at negative 6.25 and includes that point and goes up from there. This parabola exists only above y equals negative 6.25. So finally, to find our x and y intercepts, we'll start with the x-intercepts. And I will say for sure that there are 2 of them. So remember, the way you find x-intercepts is you find zeros. So if I calculate 0, I'll find the leftmost x-intercept first. So I'll go a bit to the left, a bit to the right of it, and then my guess, somewhere in between, around 3. It turns out that x-intercept is 3, or negative 3. My other x-intercept on the other side, I can do the same thing. So looking at that, it appears to cross the x-axis somewhere around x equals 2. So I'll let my left bound be 0, and I'll let my right bound be 4. Really give myself a big window here. And then I'll guess, I don't know, maybe I'm a little off, maybe that's 2.5. Nope, we were right the first time. That's actually at 2, 0. Now our y-intercept is going to involve a slightly different procedure. For this, I can actually use the trace button. So normally we hit second trace to get to the calculate menu. We can just hit the trace button, and our cursor will snap onto the graph that we're dealing with. Now remember, the y-intercept occurs when x equals 0, so what trace allows me to do is pick the value of x, which I will let that be 0. If I hit enter, it'll jump to that point on the graph where x equals 0, and we see that occurs at 0, negative 6. So for every parabola afterwards, you can confirm all of these pieces of information in the calculator and verify your work as you're going along. So the next example that I would like to look at involves the same function, and we're cheating a little because we already saw what this graph will look like. But I am going to solve this using the procedure outlined in the notes for graphing. So that is definition 4.14. The first thing that we want to do is determine the concavity. Well, we know that a equals 1, so that tells me this is concave up, because that coefficient is positive. Alright. Secondly, we want to find the vertex. So using the ideas from the previous pages, the vertex can be found. First we'll find the x-coordinate, as opposite of b over 2a. Okay, here b equals 1, and a also equals 1. So our x-coordinate is negative 1/2. Then we plug that into our function to find the y-coordinate. Alright, so 1/2 squared plus 1/2 minus 6. Well, 1/2 squared would be 1/4 plus 1/2 minus 6. That would be 3/4 minus 6. Oh, and I've missed the negative sign. So this should actually be negative 1/2 throughout. Let's try that one more time. So negative 1/2 squared plus negative 1/2, so minus 1/2 minus 6. That looks a little bit better. Alright, well 1/2, even if it's negative, if we square it, we still get 1/4 minus 1/2 minus 6. So if we apply the order of operations, we're going to do the first subtraction first. So 1/4 minus 1/2 is negative 1/4 minus 6, which gives us negative 6.25. And there we confirmed that our vertex is at negative 0.5, negative 6.25. Alright, we'll continue this problem on the next page. Alright, well so far we know it's concave up and we know the vertex. So we could actually start trying to graph this parabola. Our vertex, negative 1, 2, 3, 4, 5, 6, and negative 1 would put us right about there, just a little bit below 6 and a little to the left of the y-axis. And our parabola is going to open upwards, so just to sort of see what we're dealing with, I like to plot the vertex and sketch out the shape of our graph. So I see that this graph from this vertex is opening upwards, so it is going to have to hit the x-axis. So at this point we could conclude that this parabola will have at least those two x-intercepts. So when we go to find them, it's not going to be a fruitless search. So let's start on the intercepts. X-intercepts. To find those, we are going to let our function x squared plus x minus 6 be equal to 0. And again, I like to start off solving these types of equations by trying to factor and seeing how that goes. So can I factor x squared plus x minus 6 into binomial terms, or factors rather? Well, let's try x and x. That's the only way we can get x squared. And then I'm thinking of factors of negative 6, which would add up to positive 1, the coefficient of x, the middle term. So 3 and 2 seem like good candidates, and I think 2 is going to have to be negative and 3 is going to have to be positive. So if we want to make sure that works, is x plus 3, x minus 2 equal to our function? Well, if I FOIL this out, we get x squared minus 2x plus 3x minus 6, which simplifies to x squared plus x minus 6. So that's our factorization, which means I can then solve each piece being equal to 0. So if x equals negative 3, x equals 2, then our function is zeroed out. We get 0 for y when x is either one of these two values. So let's plot those as well since we've got them. Negative 1, 2, 3. 1, 2 in the positive direction, both on the x-axis. And then our y-intercept is going to be even quicker to find. Remember the y-intercept, if you let x be 0, we get 0 squared plus 0 minus 6, so negative 6. And our y-intercept is at 0, negative 6. Okay. So our parabola opening upwards is looking good. Now, one nice feature of these graphs is their symmetry. So if I know that the axis of symmetry passes through the vertex, I can plot that. And then this point, 0, negative 6, is half a unit to the right of the vertex, to the right of the axis of symmetry. So there's going to be a matching point the same distance to the left of the axis of symmetry. So we get the point negative 1, negative 6 essentially for free. And that comes in kind of handy when we don't have as many points to pick from as we do with this graph. And we'll get into an example that illustrates that point in just a minute. Okay, so here we see another parabola that we would like to graph using that same procedure. First, we'll determine the concavity, and we see that A equals 1, B equals 2 in this case, and C equals negative 24. So our concavity determined by A is going to be upwards, so we have a upward opening parabola. Then we want to find the vertex. So remember, the vertex is going to have an x-coordinate of opposite of B over 2A. So B, we said was 2, and A, we said was 1. So what does this simplify down to? Well, our 2's cancel, and we just have negative 1. And then y is going to be nice. We just plug negative 1 back in to our function, to our formula, to find y at this point. Negative 1 squared plus 2 times negative 1 minus 24. That's negative 1 squared is just a 1. Negative 1 times 2 would be minus 2, minus 24. So it looks as though our y-coordinate is at negative 25. Alright, then we'll get into finding all of our intercepts. Okay, our x-intercepts we find by setting y equal to 0. And let's see if we can factor this one. We've got x squared, 2x, and negative 24. So again, I'm looking for factors of negative 24 that add up to 2. So I'm thinking a 4 and a 6, and I think the 4 needs to be negative and the 6 needs to be the positive one. So from there we can say x equals 4. If we solve that resulting equation, that factor being equal to 0 implies x equals 4. And this other factor implies x equals negative 6. So we've got our x-intercepts, 4, 0, negative 6, 0. And our y-intercept, remember if I plug in 0 for x, every term with an x in it is going to go to 0, so we're just going to get the constant. That's a nice little shortcut you can take with these polynomials. The y-coordinate of the y-intercept is always just going to be that constant at the end. Alright, well that should be enough for us to graph, so let's put that all together. Got a pretty extreme graph. We want to be able to see down as low as negative 25. And this will obviously look much better if you're doing it on graph paper, but we'll do our best. So we've got our x-intercepts, and I'll do these slightly out of order. Our our y-intercept down at negative 24, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you would like, you can always rearrange how you're labeling your axes. 14, 15, 16, 17, 18. You can let your y-ticks represent 2s or 5s, whatever's convenient. Just make sure you keep track of that. 24, so 25 right there. Alright, so we'll plot our vertex at negative 1, negative 25. Our y-intercept at negative 24. And just for the sake of thoroughness, I'll plot my axis of symmetry. Remember, the axis of symmetry is a vertical line. So 1 unit to the right of the vertex, we are at a height of negative 24. So should we also be 1 unit to the left of the vertex. And all I need to do now is just try to connect this up using a nice smooth curve, which is a little tricky considering the size of this graph, but you get the idea. Okay, so my parabola is a little lumpy. That'll obviously look a lot better on graph paper, and you can always confirm by plugging it into your calculator. So let's make sure we did everything right. Go back, clear out that old equation. We'll type in x squared plus 2x minus 24. Alright, now with our standard window, we can see this is a parabola opening upwards. We see that our x-intercepts look solid. Let me adjust my window so I can potentially see the graph that I came up with. Let's go down to a y-min of negative 30. Alright, well, it looks like our vertex is down in the neighborhood of negative 25. And you can use all of the techniques from the previous problem to verify that you ended up in the right place. With all of those data, you can find your vertex in the calculator, find your y-intercepts, confirm that your x-intercepts are negative 6 and positive 4. But we are going to move on. So here we have another quadratic to graph. We'll go about it in exactly the same way. This time we see that a equals negative 1, b equals 2, and c equals 1. So looking at a, we see it's less than 0, which implies this is a concave down parabola. This parabola is flipped relative to the basic y equals x squared. Next, we'll look at the vertex. So the x-coordinate being negative b over 2a. That would be negative, again, 2 over 2 times negative 1. This is actually negative 2 over negative 2. Our negatives cancel, our 2's cancel, and we just get 1. So the y-coordinate is going to be nice to find. If I plug in 1, I'll get negative 1 squared plus 2 times 1 plus 1. So negative 1 squared. Again, this is not negative 1 in parentheses being squared. This is negative 1 squared. So that would be negative 1 plus 2 plus 1 leaves us with 2. Our vertex, 1, 2. Alright, now let's get into the topic of the intercepts. So our x-intercept, or intercepts if there are any, we'll set our y value equal to 0. Okay. I'm never a big fan of having a negative leading coefficient, so I might multiply both sides by negative 1. So negative 1 on the left times 0, and negative 1 on the right times the rest of my function. That leaves me with 0 still on the left, and the sign flipping everywhere on the right, x squared minus 2x minus 1. So these equations are all interchangeable. Now, I'm looking at this and I'm thinking of ways of factoring x squared minus 2x minus 1. So I need x and x for sure. Then factors of negative 1. Well, really only one way of doing that, negative 1 times 1. And that does not add up to 2, so I don't think factoring is going to be the way to go here. We have an x term, so solving by the square root method is not going to work out very well for us. We can't get x squared on one side and constants on the other. So if we solve using that approach, we're going to end up with the square root of x running around somewhere in our solution process, and that doesn't help. So I'm just going to jump straight into the quadratic formula. So now we have a equals 1, b equals -2, and c equals -1. Those are the variables I'm going to use, or the parameters I'm going to use in the quadratic formula. So this equation implies that x equals opposite of b plus or minus the square root of b squared, that's -2 squared, minus 4 times a times c, all of that over 2 times a. Alright, so all we need to do now is simplify. I think -2 is going to cancel, give us +2. Plus or minus the square root of, we have 4 here from the square of -2. Minus 4 times 1 times -1. Those negatives can get really tricky, so watch out for those. The negative and the negative cancel, giving me +4 all over 2. Alright, so we have 2 plus or minus the square root of 8 over 2. And I can simplify the square root of 8. I can get a 4 out of all of that, pull that outside as a 2. And then I can factor a 2 out of every term in the numerator. And cancel with the 2 in the denominator. Oh, I'm missing my plus or minus there on the square root. So I'm really looking at 1 plus or minus the square root of 2. Now this may not be one you know off the top of your head. It's a good one to know, but the square root of 2 is approximately 1.4. And that's about as good as we need to get with that. So my x values I will approximate as 1 plus or minus 1.4. So x is approximately 2.4 or negative 0.4. That's how I like to handle these when I end up with one of these weird quadratic formula mess of a solution. I'll make an approximation just for the sake of graphing. So our x-intercepts are approximately 2.4 and negative 0.4. What about our y-intercept? Well, our y-intercept, if we plug in 0, is just going to be c, the original c that we started with. So we have a y-intercept at 0, 1. And if we put all of that together, we're going to use a nice small window here. We'll go 1, 2, 3, 1, 2, 3, 1, 2. Alright, so I'll start from the top. This is concave down. That will come into effect as soon as I start graphing my vertex at 1, 2. My x-intercepts in the neighborhood of 2.4 and negative 0.4. And finally, our y-intercept is up here at 0, 1. So our axis of symmetry tells us we can plot that other point on the other side, 1 unit to the right of the axis of symmetry, at 2, 1. And our parabola opens downwards, fitting into all of these points. So again, plug that into your calculator to confirm that we did everything right. Trace along the graph and check all of these x values. Check and make sure this graph really contains the point 2, 1. And that is all we need to do. Now, so far, all of these parabolas have had x-intercepts. So how do we handle it if we encounter one that doesn't? We'll see coming right up. So again, we've got a parabola, a quadratic equation or function that we would like to graph. Looking at this one, we have a leading coefficient of 1 again. The middle term, b, has a coefficient of 2, and our constant is 2. So we can tell right away it's going to be concave up. And let's dive right into finding the vertex. X is going to be the opposite of b over 2a, which is the opposite of 2 over 2 times 1. So kind of a common thread here. We end up with a vertex of -1, comma, we don't know yet. So we're going to plug -1 back into our function. And we end up with -1 squared. In this case, we are actually squaring -1. So 1 minus 2 plus 2, our vertex's y-coordinate is +1. So our vertex located at -1, 1. Alright, so let's just sketch this out and see what we're dealing with. We've got a vertex at -1, 1, and our parabola opens upwards. We are certain of that. Now, looking at this graph, there's absolutely no way this parabola is going to intersect the x-axis. So I can conclude right away that there are no x-intercepts. So we might as well move on. Let's find the y-intercept. And we can do that very quickly. It's going to be located at 0, 2, because 2 is our constant. Alright. So let's sketch this out. Come over to -1, 1. There's our vertex. And our y-intercept up here at a height of 2. Now 2 points is enough to define the shape of a line, exactly, uniquely, but it's not quite enough to help us out with a parabola. We know that this one opens upwards, and we know that this point at -1, 1 is the vertex. So if I sketch my axis of symmetry, I know one side of my parabola will look something like that. You can always plot more x-coordinates and find the y-coordinates associated to get the shape just right. But I will mirror that across and say there's this other point here at -2, 2, the mirror image of our y-intercept across the axis of symmetry. And that is enough to get the shape of our parabola just right. So that's where the axis of symmetry comes in really handy. And it's good to be able to talk about the axis of symmetry. So if our vertex is the point -1, 1, how would we describe the axis of symmetry? So the axis of symmetry, remember, is a vertical line and we know the point that it passes through. So our equation, remember vertical lines take on the form x equals the x-coordinate. So that's how we would discuss the axis of symmetry, or its equation. The equation of the axis of symmetry in the case of this parabola, x equals -1. So that is how you handle the case when you don't necessarily have those x-intercepts to get your shape exactly right. We have enough information if we find the vertex and if we find the y-intercept, we can get the mirror image of the y-intercept and get our graph looking just right. Now all of the parabolas that we've looked at so far have been in this standard form, ax squared plus bx plus c. The other form that our parabola can take goes back to that strange alternate version where we wrote it in terms of transformations. A condensed form for that is what we call vertex form. So vertex form, if we have a function f of x equals ax squared plus bx plus c, we could write this as a times the quantity x minus h squared plus k, where h and k are the x and y coordinates, respectively, of the vertex. Okay? So for example, the parabola we just looked at, y equals x squared plus 2x plus 2. Remember, this guy had a vertex located at negative 1, 1. And a for this parabola was 1. So we could cobble together vertex form. Here we have standard form. Our vertex form is going to involve a, so 1 times x minus h, here we have h, the x coordinate of the vertex, squared, plus k, the y coordinate of the vertex. Okay, so y equals x squared plus 2x plus 2 can be written as x plus 1 squared plus 1. Now, viewing this parabola, we now have all of the tools to figure out what the graph of this looks like by finding the vertex, determining concavity, using the axis of symmetry to fill in the details. But we've been able to graph something like this since chapter 3. This is going to be x squared shifted 1 unit to the left and 1 unit up. So we can put that together. If I take y equals x squared and I shift it 1 unit to the left and 1 unit up, we get the graph that we just came up with. And we see that our vertex is exactly where it's supposed to be. So that's why we call it vertex form. The horizontal shift takes place because of what's happening inside parentheses. The vertical shift takes place because of the constant outside. And the point that we are interested in, the vertex in particular, is shifted according to those specifications. Now, the leading term, leading coefficient, if there is something more interesting going on with A, we would perhaps see a vertical reflection, or maybe a vertical stretch or compression. So let's take a look at one of those. So here we're going to look at a parabola whose equation is given in vertex form. Okay, so the difference here from standard form, we don't have an x squared and x and a constant. We have this quantity in parentheses, x minus 4 being squared. So we can pick out the pieces. Here we have a. H here is going to be 4. Remember, vertex form has a negative built into it. So we can just pick out, if we have a negative already, h is going to be whatever that number is. And k involves adding a number. So if I'm subtracting 18, k is going to be negative 18. Relative to vertex form generally, we have ax minus h squared plus k. So that's where all of our pieces are coming from. So I can immediately tell what's going on with the concavity. This a is exactly the same as the a from the standard form. So this parabola, with a being -2, is going to be concave down. Moreover, this parabola is actually also going to be stretched by a factor of 2. If you consult Theorem 4.8 concerning vertical stretches and compressions, you'll see that the magnitude being 2 means that we're going to stretch our parabola. It's going to look thinner than y equals x squared would. Now this is nothing new. This is a vertical transformation just like out of chapter 3. So we're flipping vertically and we're stretching. Alright. Then to discuss the vertex, the nice thing about vertex form is the vertex is basically given to you. So our vertex is going to be at 4, -18. Alright. Now the tricky part with vertex form is in finding your intercepts. So before we get into it, let's see what's going on with our graph. Now this sort of getting started back in the napkin calculation doesn't really need to be that accurate. Our vertex at 4, -18, and this parabola is going to open downward. So just looking at the trajectory, I don't think we should expect to find any x-intercepts. Let me verify that in this case, because this version of a parabolic equation is a little bit strange. So to find our x-intercept, if there were one, we would let y be 0. Okay. Now, when our equations are given in vertex form, solving for the x-intercepts actually tends to work really well using the square root method. So I'm going to try to isolate x minus 4 squared, first by adding 18, then by dividing by 2. Okay. So you may be able to see where this is going. Now I'm going to square root both sides, and we get x minus 4 equals the positive or negative square root of -9. In other words, x minus 4 equals positive or negative square root of 9. Well, we could call that 3 times I because of that negative under the radical. So if I add 4 to both sides, we get x equals 4 plus or minus 3i. And that's exactly what we would expect in a situation where there is no real x-intercept. There are only imaginary solutions to the necessary equation if there were x-intercepts. So, two different ways of seeing why there are no x-intercepts, but there's certainly going to be a y-intercept. And unfortunately, finding the y-intercept in vertex form does involve more work than it does in standard form. Remember, to find your y-intercept, you're going to evaluate when x equals 0. So if x equals 0, we get y equals -2 times 0 minus 4 squared, minus 18. You can see how plugging in 0 doesn't really make anything disappear right now. We have -2 times -4 squared, minus 18. Well, -4 squared is 16, so we've got -2 times 16 minus 18. It looks as though our y-intercept, -32 minus 18, is going to be all the way down at -50. Okay, so we'll do a rough approximation get our graph to look as good as we can with limited room. Alright, we've got our x-intercept way up here. We don't need to see very high since this is all happening below the x-axis. Alright, we've got our y-intercept at negative 18, or not our y-intercept, I'm sorry, our vertex. So I'll go in 5s. 5, 10, 15, 20, 25, 30, 35, 40. Shoot, that didn't work. Let's do these by tens. Negative 10, negative 20, negative 30, negative 40, negative 50. Okay. So that would put our vertex right about there, and our y-intercept all the way down at negative 50. And again, our axis of symmetry helps us out. We can get another point 4 units to the right of the vertex, also at a height of negative 50, and that's enough to make our graph look okay.